Good evening, ladies and gentlemen. In tonight's lesson, I'm going to be doing the second lesson on Newton's laws, and we're going to be looking specifically at inclined planes and inclined plane examples, as well as Newton's law of universal gravitation. So that should round off Newton's laws. Please note this is very much a practice and calculation section, at least for Newton's second law and Newton's law of universal gravitation. So you need to make sure that you go and you practice lots of examples. Watching videos on how to do the theory and attending lessons on how to do it isn't enough alone without the practice that follows on. All right, so let's get started. Okay. I'm just quickly moving all of my bits around so that I can get going. So the section that we looked at, or the aspects of Newton's laws that we looked at in the last lesson, were Newton's first law, his third law, which are the two application only, so without calculation sections. And then we finished off by looking at Newton's second law. What I want to do with you tonight is a little bit on inclined planes. So the first thing that you need to understand is when we talk about an inclined plane, we're talking about an object that is no longer moving along a horizontal surface, but instead it's moving up a slope or up an incline. All right, so that is specifically what we're looking at here. So if I imagine that we've got a slope or an incline, I can also put in the bottom there, that's the ground, and we'd put an object usually sitting on this slope. Now, the first thing that we're going to do is going to be resolving a vector into its components. You actually did this in the last lesson. We resolved a vector into a vertical and a horizontal component. Please remember, resolving a vector means turning one vector into two vectors that are perpendicular to each other. So if I told you, for example, that I have a 5 kilogram weight on a slope with an angle of 20 degrees, the first thing that you need to appreciate is that the weight itself acts straight downwards, vertically downwards towards the ground. And that weight can be calculated using the equation of mass times acceleration due to gravity. Please note you are allowed to use Fg, which is force due to gravity, or W, which stands for weight. It's one of those ironic things where years ago we used W, and then there was a change where everybody used Fg, and at the moment there are people who are using both, but I go with using Fg. And our weight is always going to be our mass in kilograms multiplied by the acceleration due to gravity, which is positive 9,8. Okay, this is the same value as your acceleration due to gravity, and you could put in meters per second squared, but you don't actually have to do that. You can just use 9.8 as a value. So my weight here is 5 multiplied by 9.8, which gives me 49 newtons. So we have got a weight of 49 newtons acting straight down. But I can turn that weight into two components. Instead of doing one vertical weight that acts straight down, I can talk about the component of the weight that acts perpendicular to the surface and the component of the weight that acts parallel to the surface. Something that's important to note is that the angle between parallel and perpendicular is a 90 degrees that fits in there, and that this angle of 20 degrees is the same as the 20-degree angle that goes there. I practiced drawing these diagrams for years, well, not years, for a long time, years ago. And it's very important that you're able to do them. In fact, to the point where if you ask me to draw it with a slope sloping the other way, I struggle a bit, but it's really important that you can work out your components. Some people learn them off by heart, so they learn that as a rule, because the component of the weight perpendicular should always be adjacent to the 20 degrees, it will always be equal to, no, I'm just going to figure this out, it will always be equal to 49, or your weight, cos of the angle that you've got, which in this case is 20 degrees. So my component of the weight perpendicular to the slope here is 49 times cos times 20. Please make sure your calculator is on degrees, which gives you 46,04 newtons. That is a component of our weight which acts perpendicular down into the slope. Normally, what we'd then do later on, just so you're aware, is that we would say that the normal is equal and opposite to this component, unless, of course, we're applying a tension that acts upwards at an angle to the slope in addition to everything else, and then that falls through. The other thing that we're going to do here is we're going to work out the component of the weight parallel to the slope. Now, because this is usually opposite the 20-degree angle, we can say that it's your weight, which is 49, multiplied by sine of 20 degrees. Okay. Sorry. Kelly, you've written a question. Okay, will F always be the weight, or does it depend on the question? So over here, this will always be the weight and this will be the weight. Some people even get taught that FG perpendicular is equal to FG cos of the angle theta. I prefer not to teach this because I like my students to think about it, but I think we're almost at the point getting into exams where I've given up trying to teach the why, and I've resorted to going, if I have to, I'd rather you got the mark for an answer than that you fully understand the extension of y. Okay, so the weight here will always be the weight. Okay, all right, so that 49 sine 20 is going to be 16,76 newtons, and that will be acting down the slope. All right, so very importantly, if you're asked to draw a free body diagram of this object, you have a choice. It either has the weight acting straight downwards and the friction acting, sorry, not the friction, the normal acting at 90 degrees. Now, we're not certain if this has friction. It could be accelerating down the slope if there's no friction and then we don't have friction. There's a very good likelihood that there will be a frictional force that acts up the slope. Please make sure that if you ever get an object on an incline, your free body diagram also looks like it's on an incline. There was even a suggestion made at the beginning of this year, following the feedback from last year's exam, suggesting that students could very gently in pencil draw in not a force, but just kind of a guiding reference line to say, that's my slope. So very faint, thin line. Just go, here's my slope, so that everything, all of your forces look neat around it. So that is your one option for a free body diagram. Your second option for your free body diagram, instead of having the weight, could, and I'm going to quickly put the little incline that I drew in last time back in, it could instead have the component of the weight parallel to the surface and the component of the weight perpendicular to the surface and your normal. Remember, I wasn't certain if there was or wasn't a friction here or other forces, so that's kind of an optional force depending on whether it exists or not. Please note, it is a choice of this or those. If you put in both of them, you have effectively put in the weight twice, and that is incorrect. What you also need to remember is that there's not necessarily always going to be a friction that exactly equals your component of the weight parallel to the surface. So it's a very dangerous assumption to say that this is equal to the friction. That only applies if you're in equilibrium, which means either you have an object that is at rest or about to move but at rest, or an object that is moving at a constant velocity. If the object is accelerating down the slope, then you need to consider that the components or the forces acting up and down in the plane of the slope this way and this way, either one of them could be bigger. Something else that I do like to point out is that which way friction acts depends on which way this object is moving. All right, so I just quickly want to check before I move on that everybody has got the ideas that I've just mentioned, kind of understood them before. Everybody happy with those? Okay, because what I would like to do with you now is a rather tricky example based on this idea. I want to work with an object that's moving up the plane initially, so up the slope, and I want to work out what its acceleration is, and then I want to deal with the fact that if it's moving down the slope, how its acceleration would change. So it's a little bit of a tricky question, but not impossible, just different. All right. So once again, full disclaimer, I am totally making this question up. So if anything does go wrong, please just bear with me. So I've got an object, we can make it of mass 2 kilograms, on an incline with an angle, let's make this 15 degrees. And I'm going to add something in here to make this slightly more complex, but appropriate for what you're dealing with. So I'd like to first of all tell you that this object initially had a force pushing it up the slope, but the force that was pulling it up the slope was very promptly removed. Okay, so this object here is moving only under the effect of its own weight and friction. Okay, so there's no propelling force or tension pulling it up or tension pulling it down. So I'm telling you here that this object was initially moving up the slope. How fast it was moving doesn't actually impact this question. And although I do have an option to incorporate or use my equations of motion as well, by saying, here's the velocity, you work out the acceleration, then you work out how far up it goes. That's not what I want to do here. So we've got an angle of 15 degrees. I'm going to tell you that the coefficient of friction here is, let's make it 0.1. So my question here is to ask you to please calculate the acceleration of the box. Now, because I have not done this in its entirety with you before, I think I'm going to do one just to make sure that you get all of the pieces before I abandon you to try and do them on your own. So the first thing that I'm going to do, and it's not always the first thing anyone has to do, there are multiple steps that you could start with, is I'm going to work out what the weight is. So the weight is equal to m times g, which is 2 multiplied by 9.8, which gives me 19, oh, that's a very big 9. Quickly redo that, which gives me 19,6 newtons. That weight is the weight that acts straight downwards. The second thing that I'm going to do is I'm going to work out the components of the weight in the two directions, both parallel and perpendicular to the slope. So I want to work out what my FG parallel is, as well as what my FG perpendicular is. If you remember the formula that I told you just now, you're welcome to use that. So I'm going to say FG parallel is equal to mg sine theta. There it is. So this is going to be 2 multiplied by 9.8 multiplied by sine of 15. Okay, so that is the component of the weight parallel to the slope is 2 times 9.8 times sine of 15, which is equal to 5,0728 blah, 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 but I'm just going to call it newtons there. Then my FG perpendicular is going to be mg cos theta, which is 2 times 9.8 times cos of 15. So 2 times 9.8 times cos 15 gives me an answer of 18,93 newtons. I hope everybody's doing these as well at home alongside me, and checking that you agree with my calculations, because sometimes I get them wrong. All right, so that so far tells me a little bit of information. Now, if this surface has a coefficient of friction, it must be rough. I usually draw in on my diagram a little cross-hatching like that to show that it's rough. At this point, I need to work out what that frictional force is. So because it has a velocity, it is moving. So we can say Fk is equal to mu k multiplied by the normal. Now, you may find it beneficial to quickly draw a free body diagram to be sure that you've got all of the components and all of the forces. So if you wish, you may put in the little marker line just to make sure that we do things in the correct direction. Because I've already resolved my weight, I'm going to use the components of the weight because it'll be easier for me to see what's going on. So this is 5,07 newtons, and this is going to, oh, sorry, that's not going to be anything. Just take that away, that's me getting carried away. And this component is 18,93 newtons. Okay, remember that'll be 15 degrees in there. Then I have my normal force acting up. Now the normal force will equal almost always, as I mentioned to you, the perpendicular component. The only time it doesn't is if we had a tension here that acted at an angle, and then you'd have to subtract the vertical, well, perpendicular to the slope component from there. But that's not this question. That's a horrible, nasty question for another day. So over here, my frictional force is going to be my coefficient of friction, which is 0,1, multiplied by my normal, which is 18,93. And that gives me a value of 1,893 newtons, which I'm very promptly going to put in as a friction. Because the object is moving up the slope, its friction is going to be moving down the slope. So its frictional force of 1,893 newtons must move down the slope. For me to work out the acceleration of the box, I'm going to use the equation F net is equal to ma. That's Newton's second law. My resultant force, you pick a direction as positive and stick with it. I'm going to pick the direction down the slope as positive. So it's 5,07 plus 1,893. I know I've got more and fewer decimal places. It's fine as long as at the end you round to 2. My mass is back to this 2. Don't get overly confused there. And we're looking for the acceleration. So 5,07 plus 1.893 divided by 2 gives me that the acceleration is 3,4815, which just means 3,48 meters per second squared. It is positive, and the positive direction, if you remember, means down the slope. All right. I hope that that makes sense to everybody. All right. So if that makes sense to everybody, can I ask you just quickly, I've got to quickly check, somebody's asking something. Yes, sorry, there's a question here. Ma'am, can they ever ask us to work out the size of the angle? Comfortably. You'd then work backwards from either the acceleration or information that helps you to work out the acceleration. So you'd effectively start from the acceleration and the mass to work out the resultant force, and then from the resultant force, you'd eventually be able to know information about both your normal and other components, and you can work from there. There is a little sneaky sneak that you are allowed to do sometimes, but it's only for objects that are in equilibrium. Okay, so if an object here were in equilibrium, you can sometimes do a really clever calculation, and I'm going to quickly just show it to you. So if an object's in equilibrium, its component of its weight down the slope is equal to the frictional force, and the normal force is equal to the component of weight perpendicular. So that's weight perpendicular, that's weight parallel, and this is friction. And if you look here, you can then say, oh, sorry, my screen just moved itself. You can then say, well, if you look at the slope, this is equal to this, and that is equal to that. So we can effectively say here something that's a little bit unusual, but if we go backwards to this equation, we'd have a component where we can say that our coefficient of kinetic friction is equal to the frictional force over the normal force. The frictional force is going to be, if I draw a quick diagram, because I don't want to actually confuse this diagram. If I draw my weight downwards and I draw those two components this way, but it's now going the other way. So there's my friction. Here I've got to turn this around because these are all in equilibrium. So if I draw a diagram where we've got weight, this is only if it's in equilibrium, weight, friction, and normal, and that's a 90 degrees, and here we've got theta. You can see here that this is your friction, this is your normal, and if you know anything about trig, tan of your angle is equal to opposite, which is friction over normal. You can actually go and say that tan of theta is equal to your coefficient of friction. That is a cheap backward step, but it only applies if your object is in equilibrium. Okay, going back to what I wanted to cover before we got a little bit distracted. Okay, that's a trick worth knowing. Okay, if we go back to this question, Okay, so sorry, there was a question here saying why is friction in the same direction as the weight, the component of the weight? It's because the object is moving up the slope. The object is moving up the slope, the friction opposes motion, so your friction acts down the slope. Very important thing to note, if an object's sliding up a slope, its friction and its weight can both be down a slope. So if this object got thrown or pushed up a slope and it's going up the slope, it'll be slowing down even if there isn't a force being applied to cause it to move. All right. Everybody happy with this so far? I know I've been jumping around a little bit, but hopefully I didn't lose you while I was quickly answering all the additional questions. Thumbs up quickly if you're happy with this. Not quite as many thumbs up as I'd like. So what I'd like to do to add to this is I'd now like to ask the exact same question, which is to calculate the acceleration of the box. But this time I want this box to have reached the highest point in its motion and now to be coming down the slope. Now I want to show you that a lot changes and a lot also doesn't change. So if I now turn this around and make the velocity down the slope, what's going to change here is that your friction will now act up the slope. So I need to move the friction to the other side, okay? Which means, let's quickly check what else changes. Our weight doesn't change, still 2 kilograms. Still a mass of 2 kilograms, still a weight of, still 2 kilograms. So my weight is still 19.6. The inclination or angle of the slope hasn't changed. So we're not going to change that either. These two values are still the same, and I can still go and put them into the diagram exactly the same way they were. The only thing that's going to change is the direction of my normal. So my normal, sorry, not my normal, my friction, talking nonsense, the direction of my friction. Normal stays the same. It's the force of the slope or the surface perpendicularly upwards. If we go and look at the calculation we use for calculating friction, the coefficient of friction doesn't change because the surfaces themselves don't change. Please remember the coefficient of friction depends on how rough or smooth the surfaces are. Here, the normal doesn't change either, so my frictional force even remains exactly the same. So I'm going to write it in here as 1,893. This time it is going to be acting up the slope. My equation that I use of F net is MA is exactly the same. What is going to be different here, and I'm preempting that we're still going to be accelerating down the slope, or otherwise we'd have remained at rest, is that this time if the 5,07 is positive, the 1,893 will be negative. So 5,07 minus 1.893 gives me 3,177. If I divide that by 2, you'll see that my acceleration is 1,5885, which means I'm going to round that up to 9. So it's 1,59 meters per second squared down the slope. So this acceleration would cause the object to accelerate back down the slope. So just to recap, when the object was moving up the slope, the friction acted down the slope. When the object reaches the highest point, comes to rest, and gravity starts to pull it back down the slope, then it will instead have a frictional force up the slope, which means that its acceleration will be less. Will be less, because the friction and the weight or the components of the weight are in opposite directions. All right. Can I quickly ask one more time for everybody quickly just to give me a thumbs up if this made good sense to them? It's a tricky section. It's not dead easy because what we had to do here was we had to deal with friction. We had to deal with a lot of different pieces that were all brought together where you kind of had to make sense out of them. All right. So please, when you're working with inclined planes, just be very careful that you don't automatically assume that the friction and the component of the weight are equal. They're only going to be equal if they're the only two forces acting on an object and the object is in equilibrium. We can even have a situation where the weight acts downwards and we may have both a component or a tension acting in either direction, as well as friction. So don't always just assume that these two are equal. Look very carefully at each individual question that you get. Ladies and gentlemen, I'm now going to quickly clear my screen of all of the drawings because that was just what I wanted to touch on when it came to inclined planes and how to start working with inclined planes. What I'd like to move on to now, because we've got about half an hour left and we're halfway, is I'd like for us to look at universal gravitation. So some people call this Newton's fourth law, but it is Newton's law of universal gravitation. Sometimes we call it unigrav, but it's universal gravitation. Now, whenever it comes to stating definitions, I like to look at the equation that I'm using to state them. So here the equation says F is equal to G, M1, M2 over R squared. So I'm going to write down the definition showing you where I'm getting all of the parts from. So Newton's law of universal gravitation says that any two objects, pretty much in the universe, any two objects will exert a force of attraction. Gravitation can only ever be attractive. Will exert a force of attraction on each other. Oh, that should read on each other. There are no marks for that statement. The force is directly proportional to the product of, now be very careful, a lot of you are going to go into autopilot and say the charges, and then you're actually working out Coulomb's law. Very similar. Newton's law of universal gravitation and Coulomb's law are almost identical. So it's directly proportional to the product of weight. These are the masses. And inversely proportional to the square of the distance. Distance between their centers. Now, the reason that we have to specify the centers for Newton's law of universal gravitation is we're dealing with planets. Planets can have huge radii, okay? So if you were to just go and say between them and you kind of go, well, here's the one and here's its surface, that's a very small distance compared to between their centers. So that is why we always refer to the centers, because we could be talking about two giant planets with huge radii and diameters, and we don't want to exclude all of the bits in between. Important things here. F is equal to G M1 M2 over R squared. You need to know that F is your gravitational force. And it is measured in newtons. G is the universal gravitational constant, and it is 6,67 times 10 to the negative 11. It does have units, and the units end up canceling everything out so that you get newtons equal newtons, but you don't need to put the units in, so don't worry about that. Both of your masses must be in kilograms. So if you're given anything in grams, you have to convert it. Please note here, it specifically says the product of their masses. Don't write the forces directly proportional to their masses and leave off the word product, or you're going to be in trouble. And R over here is the distance between their centers. It is not a radii. So it is the distance between their centers. And that value is given in meters. So please be very cautious here. If you're ever given kilometers or centimeters, usually kilometers, make sure that you convert to meters. Also, make sure that you don't forget to square. You'd be amazed how many people mess up because they forget to square something. All right. I'm not certain if someone's asking a question. If you're asking a question, just unmute yourself and interrupt me and ask for it. All right. So this is Newton's law of universal gravitation. I'm going to check if one of my children can look for my blue sheet around the back behind me. But I wanted to just point out to you that in your exam, you are actually given little bits of information that you potentially need to be able to use. I'm just quickly going to go and see if I can get one of them while I just quickly look for a past paper formula sheet. So just give me a second while I find that. Quickly opening any past paper, because I want to show you that there's certain information that you're given in every exam that a lot of you don't think to look up, and then when you don't know what you're doing at the end, you get very surprised because suddenly they're expecting you to know the mass of the earth or the radius of the earth off by heart. You need to realize that that information is given in your formula sheet and you do have access to it, so you're never expected to know it, but they're also never going to tell you exactly what it is. All right, so if I quickly share my screen with you, okay, if you look over here, you hopefully can see that this is given in the beginning of every one of the exam papers. This is last year's May, June. So the value of G being 6,67 times 10 to the negative 11 with your newtons meters squared per kilogram. You don't need to remember the units. That's on your formula sheet. The radius of the earth is given over there, and the mass of the earth is given over here. So all of these values are given to you. Please make sure that you don't forget that they've been given to you, and then in an exam suddenly get very surprised when you're expected to know them. All right, so I'm just quickly writing these down because I actually want to prove something for you that follows on from this. Okay. Please use your formula sheets that are given. In an exam, it's amazing how much people often don't use things that are right in front of them. Also, you should note the mass of an electron is here, the charge of an electron, a large number of your constants are given, and you are expected to be able to find them and use them. All right, so that is the formula that we use to work out the force between two masses. Something to note here, this value of F is exactly the same as Fg. It's exactly the same as your weight. So please do not get confused with that. Also, the force that the two objects exert on each other, even if one is huge and one is tiny, so this mass is 1,000 times bigger than this one, the two, first of all, will always attract each other, and the force of attraction will be equal and opposite. An example of Newton's third law. The force of object A on object B is equal and opposite to the force of object B back on object A. So this force, using this equation, is the same for both of these objects acting on each other. Please do not get caught out and think that one of the two has a bigger force than the other. It doesn't. All right. So one of their favorite questions to catch you all out with is they'll go and talk about something where, and they often use proportionality. So I just want to quickly give you an idea here. They'll talk about an object sitting on the surface of the earth, and the object has a mass m and the earth has a mass me, and so it's sitting on the surface of the earth, and the earth has a specific radius. And then they say something along the lines of what is, so they'll tell you that the force in this circumstance is F. And then they'll say, if we move this object to a distance 2r above the surface of the earth, what is the new force or the new force of gravitation? And where most people get lost is they don't remember that it's not 2r from the center of the earth, it's 2r above the surface. So if we were to use proportionality here, I'm going to use everything drawn in black as for it on the surface, everything in red is for when it's further away, as you can see from my color coordinating. So F is equal to G m1 m2 over r squared. That over there is my original formula. Now, if I move it up, I'm going to get a new force. G stays the same because it's a constant. The masses stay the same because they haven't changed. But it is now going to be 3r above the surface of the earth. and we mustn't forget to square that. So if I do that, I get G m1 m2 over 3 squared is 9r squared. All of this here can be replaced with this here. So I can go and say that my new force, when it's twice the radius above the surface of the Earth, sorry, that should read new, not net, new, will be 1/9, 1 over 9 times by the original force. So if we were to make it twice the height above the surface of the Earth, it's effectively 3 times the distance. Since distance is squared, it's going to end up being 1/9 of the original force. When you move things further apart, the force gets smaller. When you move them closer together, the force gets bigger. Okay, so when we're on Earth, in reality, if you're at the top of a mountain, you actually will have a slightly smaller weight than if you're at sea level. But the difference is so negligible that we don't really worry too much about it. All right, so that is the first thing that I need to make sure you all understand. The second thing that I want to talk to you all about is the idea of acceleration due to gravity, or gravitational acceleration. This is equal to G. And I quickly want to express to all of you that this idea of G is your acceleration due to gravity. And in fact, this value is independent of mass. You should know this proof already, but just in case you don't, we can say that Fg is equal to mg. So this is the acceleration due to gravity, and please note, every planet has its own acceleration due to gravity. The value that we use of 9.8 is only applicable on the surface of the Earth. In fact, even if we start going to high mountains, it becomes a little bit less. Not so much so that we don't use 9.8, but it isn't exactly the same value that it would be at sea level. So I'm going to combine two different equations together. So Fg is equal to mg, and then the second equation that I'm going to use here is F is equal to G m1 m2 over r squared. Now I use a little rule here that big M is the planet. Little m, both this one and this one, is the mass of the object. Please note, these two forces are equal to each other. The force of gravity is the same as your weight. It's the same idea. So if we're dealing with an object placed on the surface of a planet or anything like that, the acceleration due to gravity will be the force downwards. Okay, and that'll be, let's get this right. The weight will be the force downwards. The acceleration due to gravity will be the acceleration downwards. So if I make these two forces equal, I then get the equation that m times by g is equal to g m over r squared. But these masses are the same, so we can cancel them, which then shows us that the acceleration due to gravity depends on the gravitational constant g, which if you remember is 6,67 times 10 to the minus 11. The mass, which is the mass of the planet, and r squared, in this case, is the radius of the planet. So this will be the mass of whichever planet we're on, and r will be the radius of the planet. On Earth, if you remember when I took down or showed you the data a little while ago, and I've just quickly got to find where I put it, the radius of the Earth is 6,38 times 10 to the 6 meters, and the mass of the Earth is 5,98 times 10 to the 24 kilograms. Using these, I'm going to quickly substitute them in and show that we should get a value of G relatively close to 9,81. So if I have 6,67 times 10 to the minus 11, and I put in the mass of the Earth, which is 6,38 times 10 to the 6, and I divide it by the radius of the Earth, which is 5,98 times 10 to the 24. Please don't forget to square it. You can quickly join me in calculating this and see that we get 6.67 times 10 to the minus 11. And I multiply that by 6.38 times 10 to the 6. And then I divide it by 5.98 times 10 to the 24. And I square it. Just got to make sure you square it in the right place. That did not give me the right answer, so I'm going to have to do it again. 6.67 times 10 to the minus 11 times by 6 point. You've got to be very careful with your calculator on things like this, especially when you're timesing things unusually. And then I divide it by, have I done this the right way around? Sorry, somebody's just typing something to me. I put them in the wrong order. Thank you. Brain dead. Second last lesson, and of course that's what I'll do. Let's make sure that I read what the values are instead of randomly plugging things in, because I was like, these numbers are not working. So the mass of the Earth is 5,98. Thank you for saving me. Times 10 to the 24. And the radius of the Earth is 6,38 times 10 to the 6. Let's do this correctly, because we do know what the answer should be, which is a little bit of an advantage here. In an exam, you're not always going to know what it is. Times by 5.98, silly things we do, and divided by 6.38 times 10 to the 6 squared. I still didn't get that right. I need to put in another bracket. Let's see if it's my double bracketing that isn't working. Good. I get, no, that's wrong. Has anyone managed to get the right answer from what I've done? I am not succeeding. In theory, this should work. In practice, I'm not getting it right. So just give me a second. I'm going to quickly go back and check that I wrote these down correctly, just in case that's where the silly calculation. That one is right. This one is right. That one is right. Now I'm going to go back in and get grumpy because this isn't working. This will be the one lesson we don't share for the world because I've messed up on it very badly. All right. So 6.6.
Ma'am.
Yeah, what am I doing wrong?
I'm not sure, but I got 9.79, which is, if you round it up, it's 9.8.
I know. I got that as well, but my value that I got didn't work very well. So I'm just going to try one more time, because I think what I've been doing is sometimes on your calculator, when you put values in and then you square them, it does unusual things. So I got something similar to that, but I had like an exponent there that did not work. Yay, I got it right now. Thank you. Thank you for telling me that I was on the right track and I hadn't done anything silly. So 9,799, and this will be meters per second squared. All right. Yay, so we got 9,8. Please note, in reality, I think these values are slightly rounded up because the official value that people use for G at university is not 9,8, they use 9,81. However, you use the version on your formula sheet, which is 9,8, and that is perfectly fine. All right, so we can work out the acceleration due to gravity anywhere, and we also know from this particular equation here that the mass of the object canceled out, so the mass of the object is not going to affect its gravitational acceleration. Please note, one of the things that you do need to remember with this is that all of this here is assuming, this acceleration due to gravity assumes that we don't have air resistance. So it's the acceleration due to gravity in the absence of air resistance. Galileo did experiments where he is reported to have dropped, losing words now. He has cannonballs, different size, large balls, off the Leaning Tower of Pisa, and they all had the same size, but they had different masses. And he was the first person to start looking at the fact that your acceleration due to gravity does not depend on your mass, because the mass cancels out. And the way that he saw that was when he dropped two objects and they had different masses, they'd hit the ground at the same time. What did cause them to hit the ground at a different time was the air resistance. So you've got to bear in mind with all of this that we're assuming here that the air resistance is not having an impact. There is an experiment that I usually do with my classes to actually prove this idea of the fact that your acceleration due to gravity and how fast objects fall is independent of mass. I'm not going to do it tonight, but I'm going to explain it to you so that you can all go do it at home. Imagine I have a book, a heavy book, and I have a piece of paper, a light piece of paper. This one over here is a COVID form. And I would take these two and carefully release them from the same height and drop them. I'm pretty certain that all of you right now, especially if you've got a book and piece of paper at home, I'd actually love to challenge you right now to do this, okay? So I'm going to quickly stop sharing so that I can challenge you to do this. Take the two, okay, and please not things that are very valuable, and drop them. What you should find, without exception, is that the book falls very fast and the paper kind of floats down. What I then do usually in class is I'll then say to the boys, because I teach at a boys' school, okay, so which one is going to hit the ground first? And everyone says the book. And then what I do very promptly is put the piece of paper under the book and drop them. And surprise, surprise, they hit the ground at the same time. That isn't the shocker. What gets many of them is if I'd repeated the last experiment but put the piece of paper on top, because the book is heavier, the book falls and it removes what you'd normally experience as being the air resistance that slows down the paper. And if I drop these two right now, they hit the ground at exactly the same moment. So with air resistance removed, all of the objects fall at exactly the same acceleration due to gravity. All right. Ladies and gentlemen, I think that I've managed to cover all of the essential topics related to Newton's law and also related to Newton's universal gravitation. There's quite a lot that you need to practice in terms of being able to plug in values. I think I need to go back and practice that as well and make sure that I put them in the right order, and also making sure that you use the correct units. Can I just quickly check at this point, is there anything else on this section that you would particularly like me to go over? Is there anything that we haven't yet gotten to? All right, wonderful. So I'm going to suggest at this point that you go and do quite a lot of practice. It's been reported year on year, just out of interest, that Newton's law is one of the best answered questions in physics, in spite of the number of students who find it very difficult. And I think one of the reasons for that is that many of you probably haven't gone back and practiced recently, but when you do start practicing past papers, it's one of the first questions in the exam paper, so you're likely to do it relatively early on. And that also means that when you only do half a paper, you practice Newton's laws. But year on year, it's usually the best answered in terms of how many marks people get out of the entire paper. All right, so there's a question here. Ma'am, can we do a question with tension like a Pulley question? Of course. I think that's a good place for us to finish off today. All right, so let's quickly do this. I'm going to clear everything and I'm going to give you a Pulley question. So we looked at these in the last lesson just a little bit, but I'm going to quickly use one. We've got 10 minutes. So I think we can do a rather nice one. So if I give you a mass of 5 kilograms, it is placed on, these are all horizontal and beautifully drawn, on a frictional surface with friction. And the surface here with friction has got a coefficient of friction of 0.1. This object is tied using a rope that passes over a pulley at the end of the table. And on the other end here, there is a weight pulling it down. This weight is going to be 10 kilograms. Okay. This is an inelastic rope or inelastic thread joining the two. Just thinking if there's anything else I want to incorporate here to make it harder. I think that's enough for right now. So my question to you, question 1, will be, can you all please calculate the tension in the rope? That's the first one that I want. And then question 2 is, can you please calculate the acceleration. All right, is everybody happy with what they need to do? You understand what I'm asking? All good? Okay, one of you is fantastic. I'm going to quickly pause sharing while I work out the answer. I am going to stop at the point where I get my two simultaneous equations to just make sure that you get the same. If you remember what I did when I saw you on Tuesday, I went through how you do a free body diagram for each object, how you pick the direction in which the object will accelerate, each of them independently as positive, and then how you use F net is equal to MA for each of them. Please be warned, in the last example, I did not bring friction into this question, so you need to incorporate that as well. All right, I'm going to quickly pause sharing. Please give that a go. All right, ladies and gentlemen, I'm going to quickly just share my screen with you so that you can check that your two equations are correct. Can I quickly check, has everybody got up to the point of having two equations, or am I working just a little bit faster than you? Okay, some of you are up to there. That's good. Okay, so I'm just quickly going to share with you again. So if you look at what I've got here, I worked out the weight of both objects over there. I then went and worked out my frictional force by saying that the normal and the weight were equal. I worked out that my frictional force was 4.9. So therefore, because we are accelerating towards the right here and down here, I said in this case, it's going to be tension minus the 4.9 is equal to mass times acceleration. So that's equation number one. And over here, I said this will accelerate downwards. That's the direction I'm going to choose as positive. So over here, it's going to be 98 minus T is 10A because your mass is 10. From there, I'm trying to get tension first. So I'm going to get A's equated. All right. I'm going to quickly pause sharing again so that you can carry on working further on your own, but hopefully you manage to get up to there as well. All right, if anybody's managed to calculate the value of the tension, just quickly type it in. Or shout it out, whichever you feel like. Yay, we got an answer. Okay, I did not get that answer. Yay, I got that answer. Go, Aisha. I think that's the same thing. All right. Good, good, good. So please, if you got the wrong answer, just go back and check your maths. It's usually a maths problem, and you'll know I'm an expert at those too. So I'm going to quickly show you what I did to get to the right answer. So what I did here was I made A the subject of each of the formulas because I wanted to work out tension. So I wanted an equation which only had tension. So therefore I said that this is equal to this, as you can see I did over here. Then I cross multiplied, so I times that by 10 and times that by 5. Then I multiplied in as carefully as I could. And then I had all of my t's go to one side and all of my constants go to another. And from there, I divided both sides by 15 and I got the tension. Can I have a show of hands? Who got that correct? Or who was getting there? If you didn't, please keep an eye on the maths. I know I'm being a bit of a hypocrite saying this because I sometimes mess up beautifully on the maths. But the good news is I never do it in an exam. So I'm very lucky. I mess up when I'm doing lessons with you guys, but never in an exam because I check myself very carefully in an exam. So over here, please just make sure that you check. Good news is from, and this is where the marks are allocated, F net is MA gets a mark. This bit gets a mark. This bit gets a mark. The 10A or the 5A, either one gets a mark. And then from there, your final answer gets a mark. So if you've got everything right except for the last point, you are going to get most of the marks. I think in this case, because there's friction, there's a good chance that there are an additional 2 marks possibly over there. The last question that we have to answer for today is to calculate the acceleration. So I can take this value of tension and plug it into either of these equations. I'm going to go for this one for no particular reason. So 35,93 minus 4,9 divided by 5 gives me my acceleration. So I'm going to minus 4.9 and divide it by 5. And I get that the acceleration is 6,2 meters per second squared. Please note you don't have a direction for acceleration here because the 5 kilogram object would accelerate towards the right and the 10 kilogram object would accelerate down. So usually they'll ask just for the magnitude of the tension and the acceleration, but they may ask for the tension or the acceleration of the 5 or of the 10 kilogram object, and then you'd be able to answer the question correctly with an appropriate direction. All right. Can I quickly just ask you to take a screenshot of anything that you still need before I stop sharing? All right. Ladies and gentlemen, this is the point at which we take a break before we continue again right before your final exams. Please, if you've got any questions, you're welcome to send them to me so that I can assist you if I have time to solve them. But I think that, yeah, good luck for your finals. Before that, your prelims. Good luck for your prelims. It's been a pleasure to teach you all, and I really do hope that this has made a difference and that hopefully from us covering the syllabus together, many of you are in a way better position to do your prelims and your final exams. All right. I know that this has been a really crazy year for all of you, and I really do hope that it exceeds your expectations and that your prelims are really good. All right.